as Jenny said, yeah, what I would like to show you in the next hour is some of the work that we've been doing on whole milk powder, how we look at it, where we see the opportunities, and also, of course, where we see the challenges. And I think, yeah, if we look at it, I mean, from a production process, it's fairly straightforward. It has been like it has always been. We get our milk, we separate, we standardize, we give it a heat treatment. We need to evaporate, of course. We need to homogenize to make sure that we get a stable emulsion. That we end up spray drying. We can agglomerate with lecithin. We need to, of course, control our powders. We can either put them into the fluid bed or we can put them on top of the spray dryer. And after that, it's really about storing, flushing, packaging, closing. And that should be it typically, but of course, when we look at it, even though the process seems straightforward when you put it on paper as simple as this, there's always things there to consider, there's options there to improve, there's different ways of looking at it. So, and often what we're looking at there is what is the ideal powder. Because of course everybody wants the best, but the ideal powder, on the one hand, there's an ideal powder for the user that will eventually use the milk powder. On the other hand, of course, there's an ideal powder for the manufacturer as well. Of course, if we start looking at what does the user want, I mean, it should deliver all the required nutrition. Yeah, that I want to get out of a milk powder. It should have excellent physical appearance, of course. Nobody wants a powder that's lumpy, that has started browning or anything like that. It should really be easy to handle as well, so we want to be able to scoop it, we want to be able to dump it in a container quite easily if we need it for reconstitution. We don't want to have issues there. Anything. It should be easy to dissolve. There can't really be any physical defects after reconstitution in an ideal way, so we don't want to see any fat floating on top. We don't want to see any powder particles sticking to the wall, floating at the sinking to the bottom. We don't want to see any foam there, if possible. And of course, I mean, from a flavor perspective, we don't want any off flavors, we don't want any off taste. That's all what the consumer is typically looking for. The other part, of course, very much as well is what are we looking for when we're manufacturing. And that's really, of course, delivering to the consumer what they want, or the user, but also high capacity and yield. We need to make it economically feasible, no issues during processing, and of course a good shelf life. And when we look at that and we say how do we make high quality powders, what do we need to combine? It's really the physics of the product. It's of course the process. It's about the efficiency, and that we can meet customer requirements, consumer demands, while also doing it in a cost-effective manner. And if we really look at that, I mean, what do we see? What is needed to be on top of that game? It's on the one hand, knowing what you need to know about your product. It's the physics. I mean, when we're looking at drying, when we're making sure we're optimizing capacity, we don't want any issues there. We need to know what do we have in our product. How does that relate to the physics of the product? How does that relate to glass transitions, water absorption, phase diagrams to make sure that we can get it through the dryer at maximum capacity without being sticky. On the other hand as well, are there sensitive ingredients in there that we need to protect? We need to look at that, of course, and we need to very much look at powder particle morphology, because that will depend a lot of properties at the end. That will depend a lot of bulk properties, like our density, like our flow of the powder, how easy it will be to handle. That will depend. Very much affect reconstitution of the powder as well. And of course, with what we know about the product, we have to combine that with the drying technology. So we need to get a good control of our unit operations. We need to be able to control them. We need to be able to steer them. Ideal way, we know what's there and we can model it, so we can actually predict rather than try things and see what happens. We need to know our heat and mass balances in the dryer, of course. In some cases, depending a bit on what type of powder we're looking at, we need to look at different drying techniques. And of course, in some parts in the world, particularly when it's very humid, need to look at air dehumidification to be able to do constant quality processing, constant capacity, and not have to change every time. And yeah, to be on top of the powders game, what we typically say, we need to combine that. So we need to combine what we know about the product with what we know about the technology to come to an optimal powder from that perspective. I mean, if we look at product characteristics, what is important for the powders really? I mean, it's of course your powder properties like a bulk density, a particle size distribution that you want to know, that you want to be able to control. Particle density, very important as well. From a dryer efficiency and also from a storage stability, your stickiness, your glass transition temperatures are going to be crucial in these powders. Water sorption isotops, of course. From a functionality perspective, dispersibility, wettability, flowability, always going to be crucial. Ideal situation, you can start looking at process simulation to optimize, and worst case, and that's really for troubleshooting, you might even have to start looking at computational fluid dynamics to really figure out, okay, what is happening in my dryer, where are my air streams going, where is my product going, and why am I getting particulates? And in a way, if we look at summarizing it and we say controlling product properties, I mean, which are some of the important ones that we want to control? It's typically solubility or insolubility. It's our moisture content, it's our particle size, it's vacuum volumes, like how much air do we get into the powders. And in all the cases, there's various different ways how to control that. I mean, in our process, of course, we can adjust our preheating intensity that we normally do. We can do our concentrate viscosity. Of course, we have variations in there. We can have our atomization conditions that are, of course, a major impact, and our atomization intensity. And of course, our outlet temperature is always going to be a big one there. And what we really see, of course, in many cases is there's not a single quick fix that will do everything perfectly, because we see, for instance, that if we get to the point where we increase our outlet temperature, yes, we get a lower moisture content ideal, but we also increase insolubility, we increase vacuum volume, so that's not ideal by any means. I mean, we can increase concentrate viscosity, that's fine. I mean, great for efficiency, of course, but that also comes at the risk of increasing insolubility in the product, so we need to make sure to compensate for that. We need to be able to adjust, we need to be able to say, okay, this is the product that I have, this is what I have to work with, and how can I make the best possible product out of that. And that's really about controlling particles. I mean, in milk, we have a few particles, of course, that we work with, that we control. We have our fat globules, we have our casein micelles, we have our whey proteins. I mean, they will all be in the powder, and we need to make sure that we control their stability. Otherwise, we're going to get our issues like free fat, we're going to get issues like insolubility because of protein aggregation, so we need to make sure that we control them, that we don't get any issues here, and that we get the most out of our products. Like that. One of the key ones that we typically find, of course, in milk powder manufacture, particularly in whole milk powder manufacture, want to control is whey protein denaturation. Of course, we know we heat higher, we denature the protein, and that can have positive effects, that can have negative effects. One of the positive effects in some cases is even that it can help in preventing oxidation. We unfold the whey proteins partially, we start exposing that free thiol group in beta-lactoglobulin, which actually has some antioxidant capacity, so it can help from that perspective. The other thing is, of course, the physical aspects there. The whey proteins denature, and it's very dependent on whether they associate with the caseins or whether they basically aggregate with themselves as to how that will work out. Typically, association with caseins is good. It will give extra heat stability. It will actually help your product stability. A lot of denatured whey protein in the serum phase is typically bad for stability, can lead towards insolubility. So from that perspective, your time temperature combinations that you do your heating at are going to be extremely important because they really determine how much protein do we denature and where will it go. So we need to be very wary of that. And really, I mean, we can look at all the parts in the process. We can look at every individual step. They're all important, but the key one in any of these cases is typically atomization. I mean, the part where we basically get our concentrate, we atomize it into droplets, they start drying. I mean, that's going to be the crucial part. Unfortunately, as well, it's the part that basically least is known of. We know a lot more about the drying itself. We know a lot more about evaporators, about preheating and anything like that. Whereas if we start seeing all across the world what is known about actual atomization from the perspective of what happens to our milk concentrate when we atomize, then there's still a big black box there. But of course, if we're looking at atomization, we have a lot of variables in there, we have a lot of options. I mean, we have a type of nozzle that we select, we have our operating pressures, we have our spraying angles, and we have our capacity, of course. I mean, that's really gonna determine droplet sizes, but droplet size alone is not enough. It's really about droplet size distribution. So how wide or how narrow is that? That's going to be extremely important. That's going to determine particle size of your powders. I mean, that's going to affect, of course, as well your drying air conditions. That's going to affect the particle size distribution of the powders. And really, I mean, that relates to your drying capacity on the one hand, of course. I mean, you want it to be as efficient as possible there. Your bulk density, your powder dispersibility are going to be very much determined by the atomization. Also the purity, the taste, the color, and of course your flowability of your powder. So what we typically find is, I mean, controlling atomization is really the key to controlling powder quality from that perspective. Really knowing about what product is going in. Thinking about trying to establish how is that going to behave during atomization, because unfortunately you cannot measure a lot at actual atomization conditions. Timescales are so short, shear is so high that you cannot mimic it really. So it's really about taking the right data and extrapolating that to atomization conditions, and that's where we really end up being able to control our product and our process as much as possible. Because as we said, I mean, droplet size distribution during atomization in the dryer is really one of the key operational aspects there. Because what we basically see, of course, when we look at the droplets themselves and the drying, then surface area is really proportional to evaporation rate, how quickly will droplets dry. Large particles are going to dry slow. Small particles are going to dry fast and sometimes extremely fast. On the one hand, of course, we want to avoid the poorly dry droplets. I mean, they're going to be fouling the drying chamber, they're going to be blocking rotary valves. They can give us a lot of lumping in the internal bed. We can get a lot of blocking of cyclones as well if we don't dry well enough. On the other hand, of course, if we get very small particles, yes, they will dry nice and quickly, but we're going to completely overload the cyclones. You might get plugging in the baghouses even, you could get a lot of powder emissions, and also when we look later at functionality perspectives, we don't want that either. I mean, the small particles typically dissolve very poorly, so it's really about controlling that particle size distribution. I mean, seeing where do we want to be. I mean, typically a size of a decent powder, agglomerated, 200 micrometers, something like that, very nice, but it's also about looking at the edges there. about avoiding the very small ones, avoiding the very big ones. So basically, how narrow can I get that size distribution? Can I get it to start rather than at 20 micrometers here? Can I get it to start at 50 or even at 100 micrometers? And can I get it to end at a much smaller size as well? So rather than having it running through even into the millimeters, I start controlling it. So my biggest particles are only a couple of 100 micrometers as well. And basically with a very narrow size distribution there, we get very efficient production. We don't get overloading, we don't get blockage, we can get very good drying, and we can also get excellent handling property of the powder. Of course, what we need to look at during atomization, I mean, if we want to understand what is happening during atomization to our product, we need to consider that, of course, the first thing that we end up doing there is basically forming a very thin sheet of the material, extremely high shear, of course, at these conditions. I mean, that will break up into ligaments, and that is actually going to break up into droplets. I mean, everything happens extremely quickly. Forces are very high, the shear is very high that it encounters, and that, of course, also causes issues with stability. I mean, if we look at how can we affect the droplet size, of course, the key ones are the pressure that we use, the atomization pressure, droplet size will very much decrease. We can start increasing our spraying angle, basically reducing the thickness of the sheets, and we can get smaller droplets. If we increase the capacity size of the nozzle, of course, particle size is going to increase. With viscosity of the liquids, we're going to get bigger particle sizes. We need to be careful there, of course. I mean, if we increase viscosity a lot, and I mean, if we increase solids a lot, viscosity will increase, which is great for capacity, but we need to make sure that the particles don't get too big there. Surface tension is in theory one to play with, but in practice there's not a lot you can do there from a milk perspective. And of course the density of the liquid has a big effect as well, but that's really related to your dry matter content and to your viscosity from that perspective as well. So what we really see, I mean, we concentrate on milk, we put it through a dryer, we put it through an atomizer. And what we basically see is, I mean, we get our sheet formation, we get breakup, we get a primary breakup, we get droplet formation that can even start breaking up further, so we can have a secondary breakup. And then on the one hand, of course, we can get our evaporation, we can get our actual drying happening, but we need to be wary as well that we can get collisions between particles again, and we can get coalescence, they can start growing again. So nozzle selection, crucial from that perspective, crucial to be able to say, this is the right size that I want, I get the good breakup into the powder particle sizes that I want, but I have chosen my conditions, I have chosen my angles, I have chosen my nozzles properly, so I don't get a lot of collisions happening there. I don't get everything recoalescing again before it's even a bit right and end up with very big particles. Of course, one of the key things in these powders and where the atomization has a big effect on is what happens to the fat in dairy powders, in whole milk powders in general, because what we typically see, if we put whole milk powder under a confocal microscope, we see protein in green, we see fat in red in a picture like that, and what we essentially see there is a lot more fat on the surface than we would like to see. And almost no matter what you do, you get quite a bit of fat on the surface, but we need to control that as well, because it will have effects on flavor, it will have effects on stability, it will have effects on functionality. How can you dissolve your powder, because anything with fat on it is going to be a lot more difficult to dissolve. And if we draw it schematically, I mean, what we see basically, we can find some of our initial emulsion droplets on the surface, and I mean, we can live with that. They can be there if they need to be. but it's these big patches of free fat, of surface fat that we want to avoid, and that's about controlling our emulsion stability, and that's where, of course, our initial processing, particularly our homogenization, is very important, but also what happens during atomization, because you can actually undo all the good work that you did in your homogenizer in advance by putting too much on it during the atomization again afterwards. And if we typically look at a particle like that, at whole milk powder, we look at surface composition, and we combine that, we can do element analysis on that basically, and we see an actual powder, a normal powder, normal full composition, about 40% lactose in there, about 35 fat, and about 30 protein, which adds up nicely. But if we actually look what is actually on the surface layer there, I mean, we're looking at 60 to 80% fat in there. So there's really a lot more fat there on the surface than there would ever be. Big question, of course, then is that always the case? I mean, is that just whole milk powder? Is that also other powders? Even in skim milk powder, we see something like this. A skim milk powder with about 1% fat in total composition, in bulk composition, might still have 18% fat on the surface. Very much overrepresented in there. So, and we pretty much see that throughout the whole category of dairy powders, but also non-dairy powders. In all cases, more fat on the surface there than there would be in the bulk of the powder, and it typically has negative effects on product quality, product stability, something to really look at, really control. One of the things that we typically see there, if we look at controlling free fat, emulsion stability is a very important one. I mean, smaller fat globules are typically a lot more stable, so we need to homogenize properly. The other thing we see is protein-covered fat globules are a lot more stable than normal native milk fat globules. So from that perspective, the homogenization, which actually puts the proteins on the surface rather than the normal milk fat globule membrane that's naturally there, is very efficient from that perspective. I mean, your inlet and outlet temperatures have a very strong effect on free fat as well because of temperature control, coagulation, damage to it. The other aspect that we see basically is that even during storage, even if we make powders with low free fat, it can get worse over time in case when you get lactose crystallization. I mean, you get your lactose crystals growing in your powders, bit by bit, they start damaging. Fat globules actually start squeezing the fat out, and we start getting them onto the surface. And I mean, just to look at an example, what you typically see, cyclone powders, so the smaller powder particles in milk powder, whether it's from unhomogenized or from homogenized milk, tend to have a lot more, basically, extractable fat, free fat in there, than we would have in the main fraction of the powder. So again, I mean, if we're gonna get a lot of fines, if we're gonna get very small particle sizes in the dryer, we also run a risk of high free fat on the powders. Very important there when you look at milk powder, but you can also relate that to, for instance, infant formula and other products, is that fat on the surface is free, is readily accessible for any residual oxygen that is in the in the packaging, and that is what will oxidize quite quickly and easily and can start leading to off flavors. And you can even relate that back the other way when, I mean, of course, typical ways of looking at fat oxidation is, for instance, a peroxide value that people like to measure. And what you tend to see is if your fat extraction efficiency is poor, so in cases where you only really take the surface fat out of it, you measure very high peroxide values, and you basically give an unrealistic picture of a complete product. Whereas if your fat extraction is good, you get all the fat out, so you also get all the fat in the internal out of it. That's when you get realistic peroxide values, you get realistic oxidation indices, because it's that surface fat that will cause the problems, that will oxidize readily, and that will give you issues there. Of course, it's not just oxidation that it will do. The other thing that we typically see is the more free fat, the worse the dispersibility will get, and you see that, I mean, like in an example here, you start seeing that decreasing very quickly. I mean, once you reach 5% free fat, something like that, your dispersibility quite simply becomes a nightmare, and you need to make sure that you do something about it, otherwise it's going to be a long, hard road really. So that comes back to controlling emulsion stability, making sure that it's properly homogenized, that we get stable emulsion droplets there, taking into account, of course, that a pressure drop that we get after atomization, if we go on with 200 bars and we drop that into the chamber, of course, that can have effects again on emulsion stability, so we need to make sure that it's stable. We don't get any free fat issues there, we don't get it shooting off the charts and get a big issue there. And of course we need to look at, if we see insolubility development, of course fat is one big contributor there, but it's not the only one. I mean, of course protein aggregation is another crucial one from that perspective, one that will really have a big effect. And it's really a matter of looking where will that happen. And I mean, work that we did at NISO years ago basically is start looking at different moisture content, so in dry powders, but also in concentrates, start doing heating experiments on them and basically start seeing, okay, at what point do we really start detecting insolubility development. I mean, if we do something like that on a dry powder, 3% moisture or something like that, nothing will happen. I mean, we can heat for extremely long times before we see anything happen. In the same case, if we do it on concentrates, I mean 50% moisture, 50% dry matter. Again, we can heat our systems quite long. I mean, we get a quite extreme heating conditions. Couple of minutes at 85 degrees, a minute at 95 degrees, and even there's very little insolubility happening. It's really in that intermediate stage, so it's really when you start taking out a bit more water, you get into that range of 30%, 10 to 30% moisture. I see it says dry matter on the slide there, it should say 10 to 30% moisture. That's where really the rapid insolubility will start creating. So it's really that point where you've taken a good bit of water out, but there's still quite a bit left. There's enough mobility there still for the proteins to aggregate, to destabilize. Of course, your temperature is still reasonably high at that point because it has concentrated quite far, your pH has dropped, and that combination will determine a lot of your insolubility development, and that's of course a lot related to the temperatures that you're using in your dryer, but also how with the solids content that you go on to the dryer with. Because of course those initial stages when the powder particle is in the dryer, temperature will be a bit higher. And if it's very concentrated already at that point, then you can get insolubility happening there as well. And of course, when we look at insolubility from this perspective, we need to distinguish. I mean, if we do it in skim milk, then it's nice. It will all sediment to the bottom. We get a sediment there, and we call that insolubility. If we do it in whole milk or also in infant formula or any systems that contain quite a bit of fat, then it's not just a sediment. It's also particles floating on top. It's particles sticking to the side of the wall. And when you put them under a confocal microscope, what you can really start seeing is some of that insolubility. It's really a protein matrix with also destabilized fat in red in there as well. So all that coagulates, and that may stick to the wall, that may, if it's dense enough, sink to the bottom. If there's a lot of fat in there, it may also float on the top. but that's how we typically see insolubility manifesting itself in products. And of course, since it's very much related to heat load, and the heat load is very much related to how the powder particle will go through the dryer, what we see is strong correlations there with a particle size as well. So what we typically tend to see is bigger powder particles tend to give higher insolubility from that perspective, of course. I mean, they take longer to dry. They get a higher heat load in general. They have a much higher chance of developing insolubility. Whereas the smaller powder particles, they don't suffer as much from it. But, of course, they give us other issues. We saw earlier that they have higher free fat. We see as well that they can be difficult to dissolve quite simply from the perspective of a very high surface area, so we need to be careful with that. But the nice thing you can do once you start making these relations is effectively start modeling what will my powder particle size, what will my different temperatures do, and start predicting insolubility development in systems like that. And that's what one thing we've been doing in model-based process optimization, so really see at, okay, rather than optimizing with trial and error, how can we actually predict what's going to happen? And I mean, that can be for when we start putting different formulations on or change conditions. The other thing you have, of course, often is changing weather conditions. I mean, big changes in air humidity can have very large effects there as well that we need to take into account. So how can we quickly adapt to different settings there if we know that our air humidity is increasing a lot and we want to prevent fouling, or if we know that we're going to have very low humidity. I mean, what we find as well is if we can do it with models, we can start doing some of this process optimization. We can start looking for the boundaries a bit more rather than saying we very much stay on the safe side. So what we have for that, what we've used a lot is a platform that we developed, a Nisopremia platform that has a drying module in there, dry spec, and that really allows us often to, quickly find opportunities, quickly find optimizations, and use it like that. And I mean, basically, what we look at there, overall mass balances, overall heat balances. So, of course, input parameters are typically the feed coming in terms of flow, in terms of temperature, in terms of composition. We need to know our powder properties, of course, as well, that are coming out. We know what's coming in from air, we know what's going out from air, and we can start putting that together and start predicting, looking at what's happening, start looking for more optimal conditions. So, for instance, our insolubility index that we spoke about earlier, we have put in there, and we've used some of these data to really start predicting, okay, what is going to happen? I mean, of course, what is going to happen when I increase my heat load? I'm going to be denaturing more whey proteins. It can increase my viscosity. It can actually start increasing my instability of the system to heat. And how can I basically select optimal conditions? So you can start looking at what we saw earlier. What droplet sizes will I get? What risk if I increase my viscosity because of heating, for instance? What droplet sizes will I get? How will that relate to insolubility development, and how should I adjust drying conditions? Whereas if I know if I do a heat treatment, my droplet size is going to increase maybe from 60 up to 120 micrometers. I mean, I know that's going to give a massive increase in my solubility development, so maybe I should drop my temperature a bit to compensate for that and make sure that I stay in the safe zone. So by using models like that, we can actually play around with it a lot, get the right insights, and be able to choose the right conditions. Of course, can apply them as well for other issues. And one of the ones is, of course, controlling water relations. It's really about controlling fouling in dryers. It's making sure as well that powders don't get any issues during storage from flowability issues, or in a very extreme case even caking and browning. That can happen as well in the powders. And one to really take into account there, to really look into there quite typically, is the stickiness of the powders, because that's of course an extremely important one to make sure that we can optimize dryer capacity and without running into any risks. So that's one that we look at a lot, and where we basically say we can look from what's coming into the feed, what's coming into the air. We know what our outlet air is. We know what we want from a powder. What we need to know is, when is that powder going to be sticky? At what time temperature combinations do we run into a point where the powder is so sticky that it will stick to the sides of the wall, or it can start sticking in the fluid bed, it can start lumping and caking there, and we need to start controlling that. So typically measure stickiness curves, where we take the powder, we, as a function of water activity, relative humidity, measure temperatures at which it becomes sticky, or as a function of temperature, measure at the relative humidity at which it becomes sticky. Of course, we know our relationships as well for our air quality, or the humidity of the air, and together we can convert them into a stickiness curve, where on the one hand we see the temperature of the powder, on the other hand we see the moisture content, and we can start seeing, okay, in what zone is it sticky, in what zone is it not sticky. Basically anything on the right hand side of the line will give sticky powder, so that's very much a risk zone. Anything on the left hand side is the non-sticky zone, that's where you want to be. And once you know where that is for a specific powder, then you can really look at, well, at, okay, how can I change my dryer settings to be there? Because of course this is sticky or non-sticky, but capacity is the other issue. And you can start running your simulations and see, am I in the safe zone or not? We have a stickiness curve of a powder that we know will run like that. We can see, if we take an inlet temperature of 180 degrees, an outlet temperature 65 to 95 degrees, and we look at where are we with our powder. Yes, we're mainly in the stickiness zone, but of course we're running at very low capacity as well when we start running these conditions. We can start looking as well, if we increase inlet by 20 degrees, we increase the outlet a bit as well. We're actually going outside our stickiness zone. We run very big risks there of fouling of the dryer, very short run times, all these kind of things, so we don't want to be there. And we can start looking further, trying different combinations, and rather than having to do these in the dryer and basically, of course, running a lot of trials, creating a lot of issues, we can do them on the computer, and we can start seeing, okay, combination of 190 degrees, inlet, outlet in the 65 to 95 area. We're actually nicely in that zone where we don't get a lot of stickiness, but we run at maximum capacity, and we can make the most of our dryer. Of course, the other one as well, if we start looking at running our dryers as effective as possible, it's really looking at, okay, where can I do the savings? I mean, if we look at what is taking energy in our milk powder production, of course it's the heat treatment, it's evaporation, and it's drying. But really, I mean, if we look at total energy consumption, drying by far the most energy consuming there. So if we can reduce energy consumed there, if we can make sure that our dryer is running as efficiently as possible, then we can actually make quite some savings. In the same way, of course, I mean, if we look at capital investment, if we look at operational cost, again, the dryer is the most costly by far. So we really want to say that's where we get the most out of. That's where we need to control as much as possible. And I mean, we can do simple calculations. and say, okay, if I start varying my solids in the feed, so if I start increasing that bit by bit, I mean my spray dryer cost will start, spray dryer steam consumption will start going down quite a bit, of course, because we have less and less water to evaporate. Of course, my evaporator will go up, but the overall balance is that it will keep going down. And of course, since water evaporation really determines the capacity, the dryer output, my capacity of the dryer will increase a lot, even if I increase dry matter only by a few percent where possible. So it's really, from an efficiency perspective, from an energy perspective, and from reducing capital investment, of course, in these things as well. It's really a matter of saying, where can I make these things happening? What do I need to look at? How can I achieve maximum capacity? How can I increase my dry matter to the feed there? Of course, one of the limiting factors is viscosity. I mean, we know when we start evaporating our milk, we start increasing our dry matter, viscosity will increase, and at some point it will actually shoot up. And it will go higher and higher, and we cannot do anything anymore. Biggest problem there often is not even as much in the pumps, in the atomizer, but it's in your evaporator, in your distribution plates, where you still have very low shear rate, and your viscosity will be extremely high, because what we see with milk concentrates, and we see with any product like that, is it's very much shear thinning. So a bit of shear there, by pumping through tubes inside the pumps, in the atomizers, that will reduce viscosity quite a lot, but it's the point in the process where there's very little shear, or almost no shear, that's where our viscosity really starts getting limiting. And the crucial part there is often the distribution plates in the evaporator, but we need to make sure that we can control that. How can we make sure that we keep our viscosity of our concentrates at that point even low enough that we don't get any issues? Or how do we need to adjust design of the evaporator that we don't get these issues? And of course, I mean, if we look at viscosity of milk, skim milk or whole milk, depending on composition, with protein, of course, the biggest effect, depending on temperature, typically decreases with temperature, so that can be good. Of course, at some point temperature gets high enough again that you start denaturing whey proteins, they start aggregating, viscosity increases again. So you need to be careful with that. Dry matter content, the higher you go, the worse it gets. Protein denaturation, as I said, will very much increase whey product viscosity and the age of the product. I mean, what we typically see, of course, a milk concentrate, if we keep processing, if we reduce standing times everywhere, it's fine, but if you start leaving these products stand and settle, that's where you start getting issues as well, and you get a lot of thickening of the product happening. So, I mean, if we look at viscosity of milk concentrates, I mean, what's really the most important there is the proteins. They have by far the biggest effect on viscosity, because the proteins also bind a lot of water. So typically, I mean, for caseins, 1 gram of casein will have a volume of about 3 to 4 milliliters in milk, so that fills up the system quite quickly. We have fat, of course, on top of that as well. That will very much contribute, and we need to control them. And at some point we'll really start packing it so closely that you cannot squeeze anything in there anymore. Your system is full. So we need to make sure that, how do we do that? What do we create, and how can we control that? That we can get our system as full as possible, and that even sometimes a mixture of smaller and bigger particles will allow us to pack the system a lot more efficiently, will allow us to make sure that we can increase dry matter without overshooting viscosity, whereas if it's all the same particles, then a volume fraction of about 75% is all you're going to achieve. As I said earlier, heating conditions, of course, when we denature whey proteins, the viscosity is going to increase as well. But the manner in which we denature whey proteins is going to be quite important there. One comparison that we did here is on concentrates, different solid, we had concentrates, different solids content from milk preheated with a DSI or milk preheated with a plate heat exchanger. Now we chose conditions to be sure that we got the same level of denaturation, but even despite having that, we saw quite some big differences between viscosities of the product, and typically saw that systems with a plate heat exchanger that were preheated with a plate heat exchanger gave much higher viscosities than those preheated with a DSI. As I said, total level of whey protein denaturation is very much similar for those who that could not be the difference, but looking at where does the denatured whey protein go? Does it go onto the casein micelles or does it stay in the serum? Had a very big effect there and really made a big change there to where does it go, how do we control it, and how does that make sure we create viscosity. What we saw basically, the one preheated with the DSI gave a lot of, only a small amount of whey proteins associating with the casein micelles, a lot of the rest basically being small particles in the serum, and they can very efficiently pack between the casein micelles and give you less viscosity from that perspective. So very important to choose conditions right if you want to do something like this. Of course, some other effects as well. It's not just whey protein denaturation that will affect that. It's also pH that is going to be very important in controlling viscosity of the concentrates. I mean, salts as well. We looked at adding different salts, and we can even see that calcium, magnesium, and even zinc, for some reason, could reduce viscosity quite a bit. Of course, need to be careful there as well, in that they may reduce viscosity, but they can also give some issues with stability there. I mean, your heat stability, of course, doesn't get any better with that. It provides interesting directions of how to control your systems and how to be able to make sure that you don't exceed your viscosity. Of course, as we said earlier, when we're looking at these powders and we start increasing our dry matter content, I mean, we cannot just simply put it on the dryer. That's what we did here. Just as an example, say we put it on the dryer. Basically different solids contents from low heat, medium heat, high heat powders. And they have different starting viscosities, of course. And we put them on the dryer. 180 inlet, 95 outlet. And we see that our more viscous concentrates start getting a lot more insolubility. Same way, of course, when we dry to the same moisture content. So we dry them all to 4%. And what we see is in the high heat samples, it's not too bad. I mean, we've actually prevented some insolubility development by pre-controlling our whey proteins, but in the low heat powders, we see a very strong trend that the higher the viscosity of the inlet, of course, the bigger particles we create during atomization, the more insolubility we're going to create there. So we need to be very careful there, as we said, that okay, if we do something like this, it's great for increasing capacity, but we also need to adjust our drying conditions and our atomization. So on the one hand, it's of course very tricky that when we start looking at increasing dry matter, and it's a matter of where to start. I mean, we don't just want to change our dryer, we don't just want to change our evaporator. What nozzles to select is one of the big ones, of course, and it's really about choosing a structured approach if you're going to do something like this. What should you do? What can you do to make this happen? And again, like we said earlier, atomization is really the key in all this. I mean, we're going to get a very different feed if we go to much higher solids contents. We're going to get a very different feed coming in there that's going to atomize very differently, and of course that's going to dry very differently. So we need to make sure that we control our atomization to make sure that we don't get any issues there with particles that are too large, with a lot of fines that are being created, with any issues like that, to make sure to keep a good powder. So as we said earlier, it's really about looking at controlling a particle size distribution then, so make sure that we avoid the very small particles, because they will be blocking the cyclones, they will have big effects on product properties. We should also avoid the very large ones, because they will really give us long drying times, high heat load on the product, a lot of fouling there, and a lot of issues from that aspect. So some work that we did at NISO together with Dial over the years was really looking at, okay, how can we get this done? How can we actually get the right approach towards high dry matter feed on the dryer? And on the one hand we said, look, evaporating further is the issue. Get enough capacity on your evaporator. You can probably do it. You can get that higher dry matter, but you need to know how that product is going to behave like when it gets into the dryer itself and it's being atomized there. That was really about, okay, what viscosity will it have? Because that's one of the key ones. Can we extrapolate that as well, of course, to what it actually has in the dryer? Because shear rates in the atomizer there in a dryer are in the order of 10,000, 100,000 per second, and that's something we can never measure in a lab properly. On the other hand, of course, temperatures are going to be higher as well during atomization in the dryer than what we can safely and typically measure in the lab. So we need to be sure that we can extrapolate that. Then of course you want to see what nozzle should I select. So how can I do that? The most accurate, a lot of nozzle selection that we get from our suppliers typically is done on water, which doesn't tell us an awful lot, because we need to know what's going to happen when we put our actual liquids through it, when we actually have airflow through it. So what we ended up doing there is basically doing particle size measurements in the spray in the pilot plant, and basically use what we get out of that and verify that and say this is how we can apply it in the actual drive. So just to run you through it for a second, what we did here basically is use our dryer in the pilot plant. A nice multi-stage dryer, about 250 kg water evaporation per hour, so not full commercial scale, but still decent scale to give you very realistic insights, with the evaporator of course there as well. We could make skim milk concentrates at different solids contents and measure viscosity of that. As we see, it's very much shear thinning, as we always expect to see, and viscosity decreases with increasing shear rate. The question is then, of course, what is it in the nozzle? Because with our rheometers in the lab, we can go up to a shear rate of about 1000 per second. If we want to know what is happening in the nozzle, we're pretty much here. We're pretty much at 100,000 per second. So we need to extrapolate those data to get a good idea, and you basically see, your viscosity will be dropping another order of magnitude by that point. That we need to know. The other thing is, of course, what is our effective temperature? In the lab, we can measure at 50 degrees, we can measure at 60 degrees, no problem. Given the time scales of the measurements, we cannot really measure any higher, because other changes would be happening and the sample might be thickening because of the long time scales there. So, but what we do have installed in the system as well as an inline viscometer, where we can actually measure the shear rate. It measures only at a single shear rate at about 1000 per second, but we can measure as a function of temperature. So combined with the data from the lab, we can actually extrapolate and see what would it be at a given condition when we're atomizing, and we assume a shear rate of maybe 100,000 per second. What we ended up doing there then is basically saying, okay, how can I know my droplet sizes then? What atomization conditions do I need, what nozzles do I need to get optimal sizes there, what we ended up doing there. Apologies, there was a movie, but that's not working, unfortunately, but we ended up doing particle size measurements inside the dryer there, basically looking at different nozzles, of course, looking at different different orifices there, looking at different pressures, temperatures, anything like that. And you can really measure your atomization, and you can really start getting decent measurements of your feed and see how it atomizes. Only issue there is, well, if we put milk on that, then our particle size analyzer will be fouling in 2 minutes, and we cannot take any measures anymore, so we needed to think of something else there and really say, okay, if we take glycerol, a very well characterized sample of course, then we can actually use glycerol water mixtures. They're independent of shear from a viscosity perspective, so we can actually get them at the right viscosity by simply measuring at room temperature. We know the temperature dependence there, and we can make a very nice model system that we can use to look at atomization, to look at seeing what's going to happen when we change nozzles, when we change pressures, feed rates, anything like that. And really select, okay, if we're going to have a sample with a certain viscosity, what is going to be our most optimal combination. And of course, what we get out of that, what we like to see is our different particle size distributions. And really start looking at, okay, what is the most optimal one here? Okay. And just 3 different conditions compared there, A, B, and C. What we basically see, C, it gives us a lot of large particles there, so we don't want to use that. That's going to give us issues. A and B don't give that. They nicely narrow down here the way we would like to see it. A is a lot smaller from this perspective, still quite a bit more small particles, and to really start saying, okay, using a system like this, B seems to be the preferred combination. Of course, the next step was really as well to start making milk powders with those combinations and look at, does it work? Can you push it that far? And the good thing was yes. If you push it a bit too far, you can actually start seeing issues. Under normal conditions, what we nicely see if we put it under a scanning electron microscope is some nice and agglomerated powders that will dissolve well, pretty much spherical particles that are agglomerated. If you start pushing that, not retaining, or it's not getting back to the spherical shape again. So typically a good way of looking at microstructure and seeing where are your particles. Of course, overall from a perspective of what type of milk powders am I created, what type of powder particles am I creating, electron microscope. Microscopy is a fantastic tool to really see, okay, is it agglomerating nicely? Also, is it, well, just powder particles sticking together, or do I get a lot of fusion? In some cases you see that it's not particles sticking together anymore, but it gets one big core of a particle. And it seems like a lot of droplets have agglomerated. And from that perspective, that will give you poor solution. So it gives you great insights to really put them under the microscope like that. So just taking it back to the start, just to finish off, I think when we look at these powders, when we look at whole milk powder or any other type of powder, of course, we have user properties that we want to meet, which is of course, delivering what it should deliver, giving a perfect powder that looks good, that feels good, that tastes good, that gives us no issues really from that perspective. On the other hand as well, of course, when we're making these powders, we want to make sure that we get great capacity and yield. We don't get any issues during processing. We want to get a shelf life. It's nice to get a powder that's okay for 2 weeks, but we can't do anything with that. We need to have something that's stable for a long time. So from our perspective, that's really about knowing what you're doing with the product. And looking at that, looking at the physics, looking at the interactions, looking at the powder particles, combine that of course with the technological side, with your drying. What do you know? What can you measure? What can you actually start predicting? And once you combine the two, you can really start getting the most out of it from that perspective.
So, here we are. Yes, lumps remain at the bottom.
Ah yeah, lumps remain at the bottom. That, I mean, typically what we see there, it's typically surface issues with the powder particles, and they start wetting slightly, but the water is not really penetrating, it's not really dissolving, so you get your powder particle starts becoming a very soft gel that actually starts aggregating and sinking to the bottom typically. One of the big issues that we see there is protein aggregation is the big one to control. And that's quite often whey protein denaturation in combination with casein aggregation, relating a lot to heat load during processing, but depending as well, I mean, in milk powder manufacture, of course, it's heat load during processing. If you relate that to other powders, more composite powders that are made from milk powders and other ingredients. So if you look at infant formula clinical formulations, then there's a lot of ingredient quality as well that will determine that.
Right, so Rob has asked, are there any comments on difference between spray and disc nozzles?
Typically, of course, what we see mostly being used at the moment is the nozzles rather than the discs. It's really a matter of looking at what type of liquid do you have going onto it. Very viscous systems, then of course the disc atomization gets very interesting. From a dairy but what we tend to see there is a lot more vacuole forming inner powders typically, unless we control it very well. So for whole milk powder and most systems like that, typically nozzles being the preferred option, although the advantage that you can get with discs is less damage to your fat from time to time. If you have issues there, and the disc tends to be a bit more gentle on the emulsion droplets than the nozzle.
Right, very good. Now, I think Gavin was typing something, yes? Can you use calcium to decrease your viscosity to increase your solids that you feed in the dryer?
Yes, small amounts in a controlled manner. It can be used. We've done a few trials with that over time. That where you have to be careful there is what we saw is small amounts doing it in a controlled manner help us. Of course, adding a bit more calcium will decrease your viscosity further, but it will also reduce your heat stability a lot, so you get insolubility issues happening there. So that's really a matter of controlling it. And from that perspective, pH is of course another one to consider and to play with a bit.